We're recording. Hi, everybody, and welcome to the Fast Code seminar. Today's talk is one in a monthly series of virtual talks on the latest topics in the theory, practice, and teaching of software performance engineering. My name is Bruce Hoppy, and along with Julian Shun, I co-chair the organizing committee for the Fast Code seminar, and I lead community outreach for the larger Fast Code project, of which the seminar is a part. Before Julian introduces our speaker, I'd like to take just a minute to let you know about the Fast Code seminar and the larger Fast Code project. I'm going to put a link into the chat, and I'm going to share my screen. Give it back to you in a moment, Guy. I think everybody can see the Fast Code website. Yes?
I don't think you're sharing your screen.
I'm sharing my screen. So Fast Code is an open source community dedicated to advancing software performance engineering. At this website, you can learn all about Fast Code. And I'm just going to quickly scroll down and you can see Fast Code seminar is one of the things, one of our featured events. In addition to today's talk with Guy, we have a couple on the calendar upcoming. Mike Spear is going to be speaking on June 16th. Renato Warneck is going to be speaking July 14th. And we're finalizing a talk in August. You can see previous seminars. And we are definitely interested in nominations for future speakers. Many thanks, by the way, to the organizing committee, which you see listed here. Jacob Lackey, Roberto Palmieri, Christian Schultz, Yihan Sun, and Julian, of course. So if you want to nominate someone to speak for a future seminar, please let us know. In addition to the seminar, another thing that's happening as part of Fast Code is the Fast Code blog, which is published on Substack, and I encourage you to take a look. And if you have something you're working on that would be great to promote to a broader audience, we would love to hear about it and help write about that on the Fast Code blog. I will leave it at that and turn things over to Julian to introduce our speaker.
All right. Sorry about the background noise. I'm at a coffee shop. But yeah, I'm very happy to introduce Guy Blelloch as our speaker for today's Fast Code seminar. Guy's the UA and Helen Whitaker University professor at Carnegie Mellon University, and he received his bachelor's degree from Swarthmore College and a PhD from MIT, and his research focuses on algorithms and programming language design, and especially how they interact with each other in the parallel setting. I had the pleasure of working with Guy for my PhD thesis. Guy was my PhD advisor, and a lot of the work that I've done was inspired by his research. Guy's received many honors for his work. He's an ACM fellow. He received the IEEE Charles Babbage Award, the inaugural ACM SPA Parallel Computing Award, as well as the Adrian Harris Analogic Theory and Practice Award. Today, he's going to be talking to us about his recent work on concurrent data structures. So I'll turn it over.
Okay, thank you. So do I have to share again?
I think you have.
Yeah, you need to share again, Guy. I took
It's
the
not
screen
letting.
away from
Sorry,
you.
it's not letting me share.
It's not letting you share.
I see. Okay, I see. Yeah,
You're a
it's letting me have-
co-host, so you should be able to share.
Okay. Oops. Wrong one.
We're
I
looking
took
at a
the wrong
paper.
one. On bipartite matching, yes. Yeah, now it's disappeared from my. Okay, I found it. It is paused. How do I unpause it? Resume. Okay.
I'm guessing it's
Not-
paused.
Yeah, not seeing anything.
I'm guessing that it's paused inside your presentation software.
Okay, hold on a sec then. Yeah, I see. I have to basically close it
It was
again. And
definitely working before.
no,
no.
it'll work now.
There
I
we
have to
go.
move it out of slideshow and then back into slideshow. There we go.
Perfect.
Okay, well, I'm glad to give a talk here, and please feel free to ask questions on chat. I think Bruce will yell out when questions come up. So I'll be talking about concurrent data structures and some techniques to make them simpler and efficient. This is joint work with several people, which are listed there. So just some motivation. I'm not going to do a hard sell on concurrent data structures. Hopefully, most of you believe they're useful. There's a long history of concurrent data structures. And in particular, if we look at so-called lock-free data structures, which is sort of the gold standard of concurrent data structures, that basically mean they are guaranteed to make progress even if some of the processes, stop or swap out or whatever. So if you just look at sort of the history, it's maybe a little depressing in how little progress we've made. That stacks and queues, which are sort of what we teach high school students or our first year students, they weren't sort of correct stacks and queues. In fact, there were incorrect ones earlier than this, but until around the mid-90s, linked lists, which are, again, extremely basic data structure, didn't happen until 2001. BSTs, and with no balance didn't happen until 2010. BSTs with balance, now with 2017. And then BSTs with more interesting, operations than just insert and delete and find was, a year after that. And then we're looking at, more sophisticated data structures like KD trees or something, which again, in the sequential world, KD trees have been around since the 1970s, but these are sort of state of the art in concurrent data structures. The point being is it's not easy to make correct and efficient versions. Now, in some of these cases, there were non-efficient versions before these, but these are ones where it's competitive with sequential code in the sense you actually expect to get sort of speed up if you're running on 8 processes and there's not too much contention. You hope to get somewhere close to 8 times speed up over whatever your favorite sequential version of these data structures are. So that's sort of where we are. So what we've been looking at in our group is, yes, we can, do one data structure by data structure, one after the other, and it's probably a good pathway to get dozens of papers. But it seems more appealing to sort of find some general approaches that make the whole process easier. So we can generate these, lock-free data, concurrent data structures more quickly, while not losing in efficiency, or maybe losing a little. You might be willing to lose a little bit in efficiency, but not a lot. Ideally, 10% is probably okay. Factors of 3 to 5 are surely not okay. And so the question is, are there such techniques? And maybe we should be spending more time on them than on specific data structures. So I'm going to be talking about, well, our group has sort of worked on 3 such techniques. I'm not going to talk about the first one because Yanhao Wei spoke about it at the Fast Code seminar a couple years ago. I'll just give a couple slides on it. So I'll concentrate on the next 2, which are the lock-free locks and the big atomics. And the big atomics are sort of new work, and in fact, it's as yet not published except for an archive. So that's the plan. And so let me start. So first I'll just give, again, like I said, a summary of the version pointers and what they are. So the goal of version pointers is, often on something like a BST or, more generally on a ordered set, you might want more complicated operations than just insertions, deletions, and finds. You might want to return all the keys in a range. You might want to find simultaneously the previous and next key. And it's important these are atomic. So if I do this operation and insertions and deletions are happening, that they linearize, that it looks like it happens atomically. Or I might just want to search for k distinct keys. And again, what makes this hard is the fact that it has to be atomic. So yes, I could just do k searches, but then they would not be at the same point in time normally. So these are not possible with the structures I previously listed, except I guess I did mention the range search in one of the data structures. Generally, they're not available. So our goal was to make these easily available with very small changes to existing data structures. The goal here is we can just take an existing BST, touch it up a tiny little bit, and then we get one where we can make all these queries in an atomic way. And we do this with this magic function called with snapshot, which is you basically pass it it's a higher order function. You pass it another function, a thunk, and it runs that thunk on a sort of the state in some sort of frozen position. So it basically takes a snapshot of the state of all the variables that you own, and then runs that code on that snapshot. So if you imagine like taking a range query, well, then I can just, in fact, run my sequential range query on it, and it's on a snapshot, and that would work. And same with previous and next. I can just run any sequential code for previous and next, so I can run any sequential code for searching k distinct keys, and it'll give me them all at the same point in time as a snapshot. So we built this library called verlib based on this ideas. And it uses multi-versioning on the hood. I'm not going to have time to talk about it because, like I said, I'll focus on two other things. But just to give you a sense, it's a very simple interface. All you have to do is declare your pointers to be these version pointers. You can basically think of this as an atomic STD atomic on the pointer type, so the T star. And then it just supports, load and store and compare and swap. And the point is that these are now, so you just take your existing code and plug in this version pointer, replace your T star with a version pointer and run these loads and stores. There's a couple other little things you have to do, which are listed there. And then you just run your function, some read-only function. It's in fact just some sequential code inside this with snapshot, and it'll basically run it on a snapshot of what's going on. So that's the idea. So again, this is meant to be a sort of a general technique to make it much easier to make, these things like range queries. The point is these operations take constant time, the loads and the stores, and this function runs in state. When you do a run snapshot, the time it takes is basically just the time the sequential code func takes, plus the number of concurrent updates that happen during the, while you're running the with snapshot. That's an upper bound on the amount of time it takes, theoretically. We have some experiments. This shows how, if you implement range search, and it compares it to these other ones, which are LCFA, Jiffy, Epoch, BST. These are previous data structures which were specifically designed for range searching. So they weren't taking, for example, an existing BST and modifying it in a slight way. They were designed bottom up to support range searching. While the 3 lines at the top, the ones labeled verlib B trees, are basically just taking an out-of-the-box concurrent B tree and replacing it with these version pointers. It doesn't matter what the 3 different versions are. They're just using different timestamps, techniques. But you can see they perform quite well compared to these, special purpose.
Guy, we have a question. How many cores?
I believe this one is 72 cores, 144 threads.
Thank
I'd have
you.
to go double check, but that's the machine we normally run these experiments on. Okay, so I'll spend a little bit more time on these lock-free locks. So I guess lock-free locks sound counterintuitive. So there's been a whole bunch of data structures which are lock-based. In fact, the lock-based data structures predate the lock-free ones by quite a bit of time. The earliest BST was in VLDB in 78 by H.T. Kong. B trees were from 81. These are concurrent B trees, and concurrent skip lists from 90, and mass tree is a pretty advanced tree compared to, it's a mixture of a B tree and a radix tree, and it's a reasonably sophisticated tree. The point being, it's much easier to write lock-based code, and that's why they happened so much earlier. It's no coincidence those dates on the left are much earlier than the dates on the right. But they're lock-based, which means if one of the threads stops, gets swapped out or whatever, then the thing comes to a grinding halt. So on the right are the more recent lock-free ones, which I mentioned. The question is, are lock-based, are these really disjoint sets? View this as a Venn diagram. So what does lock-free mean? It's actually a technical term. It's a term that means basically that the system is making progress as a whole, or another way to think of it is that the processes can't block each other. So it can't be that if one process, for example, has a lock and goes to lunch, the other ones have to wait for it to come back for lunch to make progress, to wait till it unlocks. So it's a sort of a progress guarantee. While lock-based is sort of just a semantic thing, just basically ensuring mutual exclusion, right? It's ensuring that one process, that there's critical sections and only one process is in that critical section at any given time. So they're sort of, not exactly the same flavor of definitions. So the question is there an intersection? And the answer is yes. So you can be lock-based, so you can ensure that there's only one process in each critical section, at least semantically, so it looks like there's only one. And you can also be lock-free in the technical sense of being able to guarantee progress, even if the threads are halting or failing or whatever. So let's look at what's in that intersection. I guess first we can talk about, well, why do we care about lock-free? I sort of mentioned this already. We care that we want to be robust against slower crash threads. There's been many papers over the last decade that show that a lot of the lock-based algorithms, as soon as you go to oversubscription, which means you've got more software threads than hardware threads, the performance decreases precipitously, significant, not just slightly, but goes down, in serious ways. And there's also other issues with locks, including priority inversion. On the other hand, as already mentioned, it's much more difficult to program the lock-free ones, and that's part of the reason why it's taken so much longer to get there. And they're also subtle and easy to get wrong. There's dozens of cases of papers, published papers, which have later been shown to be not completely correct. So the question is, can we get the best of both worlds? Ease of use of locks while ensuring lock freedom. And the claim is yes, and we can do it efficiently. And so let's look at how we can do that. Lock-free locks, well, let's just look at what, a traditional lock does. It's basically, one process, P1 and P2 are two processes. P1 it takes the lock, and like I said, it might go out to lunch, and P2 comes along and it needs the lock because it wants to run the same critical section. And it has to wait for P1 to finish. And when P1 eventually comes back, if it comes back, then P2 gets to do what it wants to do. Well, a lock-free lock, we still take a lock and it's still going to guarantee this mutual exclusion. But when we take a lock, we basically, register the code we're going to be running. So we say, I'm going to take this lock, and inside the lock, I'm going to run this code, the critical section. So this is the critical section in the scroll there. And now what happens is, well, now if P2 comes along, it knows, it can look at the code and it can say, well, maybe I can help run P1's code. I can just, run it for it. He's out to lunch, I'll finish, cleaning his room while he's gone. Therefore, I can, do the next thing. And so it can basically help P1. Now, some of you are probably already thinking, well, this doesn't sound safe. And, indeed, this is probably not safe. And this is the issue of idempotence. Idempotent means that code, that thunk that P1 was going to run, it has to look like it ran exactly once. Okay, and it's full of side effects because that's what concurrent code is all about. It's all about, reading and writing shared memory, mutating shared memory. So it has to look like it's run once, even though it's run, many times by many different processes. And not only that, but if P2 starts running this code, P1 could suddenly come back from lunch and they could be running at the same time, right? And then P3 could join too, and they're all running at the same time. Arbitrary number of processes could come in and help try to help P1. So the real challenge here is this ensuring idempotence, ensuring that it looks like that code runs exactly once, and as a a single thread. And so that's the challenge, and that's the main issue that we addressed in this particular work. That the actual idea of lock-free locks is a reasonably old idea. It dates back to the early 90s, a couple papers by Barnes and others. But their work was, in some sense, not practical at all. In fact, we don't know of anyone that's tried to implement their ideas. And there are many papers out there that basically said, oh, you could do this using this lock-free approach, but it would be horribly efficient. So we're going to do a data structure specific thing instead. And the real reason it was impractical is their implementation of idempotence. It did basically every time you did a read or write to shared memory, it sort of stored away the whole state. So you think of it as doing a context switch on every single read and write. You store away all your registers and everything, and then you restore them, and et cetera. So it was not a practical, but from a theoretical point, it's been known how to do this. So the real challenge here again is to make this idempotent efficient, and so that's what we'll be looking at. And so we developed this technique for idempotence, which we think is, experimentally is quite efficient. Theoretically, it's also efficient, and it's does well under oversubscription, and we have a library called Flock based on it, and that's a picture of a flock of birds on the right there. So how does our library? Well, the interface basically supports, two types of locks. It supports a with lock, which is a traditional lock that basically waits, semantically will wait until your turn and then run that critical section. So, in the implementation, it might help finish someone else's and then install your lock. But we actually found in code, it's often more useful to use a try lock, which is basically if someone has the lock, you basically just return false. But to make this useful, it's when you return false, you also help finish the thing that's on the lock. So if you do a try lock a second time, now it's going to be free, because the first time you went through, you said, oh, there's already someone in the lock, I'm going to help them on the lock, and then I'm going to return false. The second time through, you'll, assuming no one else has come in, you'll get that lock. And we support arbitrary nesting, and this is important because a lot of the codes we were looking at support, nested locks. So just as an example here, I wanted to show, you don't have to understand the code.
Guy, there's a question.
Okay.
Can you have repeated failed try lock?
repeatedly if other people, if there's only 2 people involved and only, then you'll fail once. You will only fail if someone else has the lock. So you help that someone else, but after you help that someone else, a 3rd person could come in before you do your try lock again, and then you would fail again. So it's lock free in the sense that you could keep failing, but someone else, only if someone else is making progress. So it's so let's not worry about the details of this code. It's basically a doubly linked list that can insert a sorted doubly linked list where you can insert, and the code for remove is not in there. You can insert and remove nodes in sorted order in this list and search for it. And so in this code, it uses a technique that's very common in in lock-based implementation concurrent data structure. In fact, this dates back to the early 1980s, called optimistic locking, is where you basically traverse the list. That's what the find node does. It traverses a list to find where it belongs, and then it just takes a fine-grained lock on the one cell that you have to lock. So if this list is 1,000 long, you're not going to take 1,000 locks. You're going to basically find the right position and then take the lock. It's optimistic in the sense that when you take the lock, then you have to make sure that your local state hasn't changed, and that's what the first 2 lines in the critical section do. But what's important here is there's this critical section. So this has to look like it's run by exactly, 1 thread when a lock is taken on that prev lock. And so, and that's the thunk there. And of course, this piece of code is doing various reads from memory, and it's doing various writes to memory. And it has to look like it worked once. Like I said, the way we're going to implement this is we're going to store away that thunk, that piece of code. And if someone else comes along and does a lock on that same location, it's going to try running it. And it has to look like it ran, however many people run it, it ran once. So that's the context here. So let's look at the implementation of idempotence to make sure those reads and writes, happen consistently. And so, we use a log-based technique. We basically, whenever you take a lock, and let's say you successfully acquire that lock, you leave along the code you want to run, and you also create this log. And this log is going to be shared by everyone that helps you finish this. Now, typically there won't be other people who help you, but if someone does, they're going to share this log. And so let's look at how this log works. It's basically going to log every time we do a memory operation. And these include load stores, and it actually also includes allocates and frees, where retire here is effectively a free. It's a safe version of free. So every time we do a load here, we're going to basically log. And so this log is just a linear log. We start at the beginning. And every time we do a load or store, we increment the count to the next position. And so what we do is, as we go through this log, and let's say P1 is going through, P1 took the lock and it's now going through running its code. It first loads, A, and if you look at the top, A points to B. And what we log is what's loaded. Okay, so we basically log this load, and this logging is done with a compare and swap, so that only one person will succeed in logging this. So the first person who tries that load, because someone else could come in and start helping, only the first person that does that load will succeed in doing the log. And then we branch. And of course, we need to make sure that everyone that runs this code branches exactly the same. So they all better have read B. Then we basically have another load, and we log what it points to. And as you can see at the top, B points to C. And so again, that's logged. And then we get to the store. What we do is on store is we log the old value. the value that was already there. So A points to B. So what we log is B. Okay, and so the store does two things. It logs the old value, and then it does a CAS, compare and swap, to A to its new pointer. So then that's the shortcut. So we basically, A used to point to B, and we now store C into it, effectively removing B. But that store is converted, in the code, it shows a store under the hood that uses a compare and swap. Okay, and in fact, for this reason, it's important that these locations ABA free, and I'll get back to that issue in a minute. But the point is that this can only succeed once, because when it does the compare and swap, it does the old value of the compare and swap is always going to be the B, and so it's going to switch from B to C. So if two people are doing this at the same time, the second will fail, because they'll try to, they'll do a compare and swap from B to C, and now the value is C, so the compare and swap will do nothing. It'll be an OR, which is what we want. We want the write to happen exactly while it runs. So here's an example. Now P2 comes in, it sees that B is already logged, so it doesn't have to do a load. And now it sees that C is already logged, it doesn't have to do a load. It gets to this thing here, it sees that there is B logged, which means it's going to do a compare and swap from B to C. In fact, it can optimize this by checking if A already points to C. If it does, it doesn't have to do the compare and swap at all. When it gets to a retire, it's going to, now it's passed. Notice that P1 had gone to sleep at this point, and P2 is now taking over the work for P1. And so P2 now will retire B, which means it'll log true, which means that now if P1 makes progress, it will see it's already been retired, and it won't double retire, because it makes sure we don't have to retire things twice. And likewise, in the allocate, we have to make sure we don't double allocate. So the first person that comes here will log, I think it's not shown in the slides, but it'll log the location that's allocated such that the second person will read that location. And so that's basically how the logging works. Now you might think that this is very inefficient, because every one of these loads and stores converts to a CAS. But you have to remember this log is in the level 1 cache of the person that's running this, because most of the time there's not contention, and so you just happily run this on your own. This whole log is in your, it's adjacent in a cache line. Not only that, but you end up reusing logs. So this whole log is going to be in your cache most of the time. And so these CASs are all local L1, hits on the CAS. It means you don't have to bring it in exclusive mode or anything of that flavor. You already have it in exclusive mode. So that's how the logging works. It's reasonably simple. So in order to convert your code to use this, you just basically have to wrap this mutable around everything that you want to be logged, and then so the next and previous and remove, which then you can think of this as sort of like an atomic, but it's this mutable atomic, and it supports loads and stores. So if later on, if you see the like remove.load, that under the hood is going to be the version that logs. And so, right, and like the picture says, it's that load there is going to commit to a log. Now, there's some loads which are not inside locks. And so loads have a conditional check that say, if I'm in a lock, I'm going to commit to a log. And if I'm not, I'm just going to do just a regular load. So the overhead for a load that's outside of the lock is minimal. There is this conditional check, but beyond that, there's no additional cost. The one issue is that it's not, like I said, we can make loads and stores idempotent. It's hard to make compare and swaps idempotent, and I'll come back to why it's important to make compare and swaps idempotent. But you can make what's called a compare and modify, and this is just a compare and swap that doesn't return a true or false. So it'll compare and swap A to B, but you don't know if it succeeds or not. So that's actually quite easy to make idempotent. Yeah, and like I said, the overhead of logging is low, especially when the critical sections are short. So yeah, so why is this CAS important? Well, it has to do with nesting. So like I said, we want to support nested locks. So the interesting thing is you can just use idempotence for the code inside the lock itself. So we don't have to do anything special. We just wrap one thunk inside of another thunk, and that inner thunk, as long as it's idempotent, will just work just fine. Okay. But the problem is the code for the tri-lock itself uses a CAS. It basically, it has to take a lock. So there's various different ways we implement it. But, here we basically CAS in some, null value for my descriptor. So here's why I basically, publish my descriptor so people can help me. Then I run my descriptor on myself, and then I unlock it, right? And if it failed, then I just help the person that has the lock. That's it's actually more complicated than this, but that's the high level idea. And so, well, first we're going to ask what the descriptor looks like. Well, it has the thunk, the code that the help is going to help. And it also has a point to do the log, because like I said, this is going to be shared by all the helpers. So that's what the descriptor consists of. And yeah, so now if we have these nested locks, well, sort of the CAS is problematic. But it turns out that you can replace it with the CAM, that you can basically just do the CAM, and then you check if it succeeded. It turns out that this by itself is not safe, and I don't have time to go through why, but you have to add some additional information to the descriptor. You have to add this done flag, and you have to check that it's not done, before you actually acquire that flag. But with that, then you can get away with the CAM. And so then the lock code itself is idempotent, so then you can just simply nest it as you want. We have a C++ implementation. It supports arbitrary length logs, which basically allows logs to grow. So it's got some fixed initial length. I think it's 8 or something, and then you can tag on other chunks of 8 after each other. It basically it's like I said, a basic technique requires ABA freedom, but you can always get rid of ABA freedom by adding a tag. And we have a way to basically implement this tag without requiring a double wide CAS. Alternative, you could just use a double wide CAS and add on a tag. We have some optimizations if your data is immutable or you're only going to update once. And then we have some various optimizations for helping. So, we compared, so obviously there's going to be some overhead from this logging. So it's not, it can't be completely free. So even if there's no contention and no helping, it means that every time you do a load and store inside of a lock, you have to do this logging, which is going to have some overhead. So we ran a bunch of experiments on a bunch of different data structures. Here, I'm just going to show one of them, which is a linked list. And it's what's shown here are 2 highly optimized, especially the red one is a very highly optimized version of Harris's linked list, which is probably the best known ordered list concurrent data structure out there. The green line is the original one, and the red line. So these are specific data structures that don't use locking. They're lock free, and quite smart how they work. The blue lines are basically a singly linked list it's a lock-based implementation using a lock-free implementation. So in fact, since it's just a lock-based implementation, we can either run it with a lock-free implementation, or we can run it with the just regular locks. And so that's what the 2 blue lines, and you can see the lock-free version is just, in the case of the lazy list, it's just as fast as the lock-based one up to the number of threads. So that's the machine has 144. Sorry, that should say those 144 hyperthreads. It's a 72 core machine, and so it goes up to and over subscription, the lock-based one suddenly collapses the performance. And again, this is kind of obvious because some threads get swapped out while they're holding a lock, and then other threads get sort of, have to wait for it. But it shows that basically for the blue one, there's the overhead for the lock freedom is negligible. For the orange one, which is a doubly linked list, the list there, then you do notice, and in several of the other data structures I mentioned here, again, you notice some overhead, before you get to oversubscription for the lock-free locks, but it's minimal. I think that's about 5% on that dotted line there. But then after oversubscription, then the lock-free locks are flat, while the lock-based ones collapse. Okay, so I think that is all I'm going to say about lock-free locks. So I guess I'm actually taking more time than I want, so I have to go through big atomics quickly. So big atomics is supposed to be another sort of general technique, or maybe it's a sort of a general primitive for building, other concurrent data structures or concurrent operations more easily. So what is a big atomic? It's just basically, you can think of it as an atomic like in C++, except it spans multiple word, structure. So you can have a structure with, 3 fields in it, 3 doubles, or whatever you want them to be. And you can load that. You can then, modify it, and then you could swap it back in, or you could do a store. Another operation here you might want to do is a store of into X. So X is this atomic, we can load it, and then we can later store it or compare and swap it. It turns out that C++ already supports this for multi-words. In fact, you can have an arbitrary long structure there. It could be, a billion words long. And C++ will support this as long as it's trivially copyable. But as I'll mention in a couple slides, it does it in extremely inefficiently. It basically just takes a lock. So I want to give, why is these multi-word atomics useful? And I want to give a few examples of applications. So first of all, if you look at modern hash tables, fast hash tables, these are sequential hash tables, like the Google Abseil and Metafolio F14 are both highly optimized. They're both, a factor of 3 better than unordered map in C++, SCD unordered map. They all do this by basically avoiding extra level of indirection. So that, C++ version SCD lib uses separate chaining, and they all use something that's similar to linear probing. They're more sophisticated than linear probing, as we'll see in a second, but they avoid this level of indirection. So just an example, the way the Foley F14 table works roughly is they basically break the table into a bunch of these blocks, and these blocks have consist of typically a couple cache lines. It depends on the particular object you're trying to store, the size of it. And then what they do is you basically just go directly to the block, and most of the time you're going to find the key that you want in the block. You hash through the block. Sometimes if the block overfills, it will propagate to the next block. But most of the time you find it in that block. So you basically go directly to the block and find your key there. And there's this header word, which actually it has an 8-bit subhash, which allows you to then quickly find where within that block you are. And so you can then access this. So this turns out to be to be very fast. And even if you have to scan multiple, keys, even if the table's filling up, you'll likely find them all, within that block, all the ones you have to check. And not only that, but it uses the vector instructions to quickly compare all these 8-bit keys to the hash. The point being that to update this, you have to update the header and the fields concurrently, atomically. You can't like update one and then the other. So if you try to make this concurrent, you have to take a lock or something of that flavor. And likewise, reading, if you update this and let's say you updated the header and you didn't update the field, and then a reader comes in, they'll get garbage and probably crash. So this has to be updated. So this is one application, is that you can actually then use a big atomic to update this whole block atomically. Another example actually goes to this multi-versioning, which is related to the first topic I talked, where you basically you maintain the versions of a value over time, so you can sort of look them up, what they look like in the back time. This useful snapshotting, it's used in database, multi-version databases. The problem is typically the simple way of implementing things just as a linked list, which means you go to some cell, you go to the first pointer, you check the timestamp. And so this involves an extra level of indirection. And in practice, 99.9% of the time you're actually accessing the first thing in the linked list. The linked list is really just there in case some update happened while you were doing your operation. And so you would like that first cell to be not involve a level of indirection. And so that's what the picture is trying to show. And so you inline that first cell. The problem with this is now you have to update that cell atomically. And so, again, a big atomic would allow us to do that. And there's several other applications, which I'll skip. So the question is, how do you implement these big atomics? And there's, actually a handful of known techniques. One is just to use locks, and this is what C++ stdlib uses, and that's why I sort of, said it's not, even though it's supported in C++, it's not usable. Another approach is to use the level of indirection. And so I'll go through a little bit more detail in a second, but you basically allocate an object, you copy your value into that object, and then you use a cas to swap it in. And it's inefficient for two reasons. One, it requires a level of indirection, and the other, it requires safe memory reclamation, epoch-based collector, some sort of safe memory reclamation, because now you're allocating these blocks of memory and you're freeing them, etc. A third approach is sequence locks, which is a way that you basically keep odd even numbers on a sequence. And I'll go into this in a second. So let me leave this until we get to the implementation. So the problem is sequence locks are not lock-free, that if a writer stalls while it's got its lock, no readers can make progress. So if a writer gets swapped out, it basically blocks all the readers. The indirection is lock-free, and in fact, it can even be made weight-free, but it requires a level of indirection, and you lose a factor of 2 or so in performance in practice if every single pointer chase you do becomes 2 pointer chases. So let's talk a little bit more about the two techniques and then how we can resolve this and get something that's both avoids indirection at least most of the time, and it's also lock-free. So using indirection, you basically, the idea is a load just reads through the pointer, but there's this extra step where you have to protect the pointer using some safe memory reclamation, epoch-based collection, hazard pointers, or something of that flavor. And then for cas, again, you need to protect the pointer. You check if the value, then you read the value, check if it equals. If it doesn't equal, then you can just return false. Otherwise, you allocate this new memory and copy a value into it. You try to, you cas in the new location. And if that succeeds, you retire the old location. And this is where the memory reclamation comes in. Otherwise, you retire what you just allocated. So here's the actual C++ code. There's a full C++ code for it. It's not super long, except this magic protect pointer and unprotect pointer, which is given here. And so, that will depend on the particular safe memory reclamation technique you use. So that's the basic idea. And there's a little picture of it above where you basically point to the old value and then you swing that pointer to the new value. And that's going to be atomic because it's just a single cas. But now, whenever you read that value, you have to go through that pointer. Okay, sequence locks are more interesting. They use a version basically, this is an incrementing version. So it starts at 0, it goes 1, 2, 3, 4. And basically, every time you update, it increments by 2. It first increments by 1, which makes it odd, which locks it. And then it increments it by another, which makes it even and unlocks it. Okay, but it's important that it's not just 1 bit. It has to be a counter that's incrementing. So here is the code. It's, again, not too complicated, but what it basically says, if let's look at the load, what it does is it basically reads the version, then it reads the value. Remember, this is a multi-word value, so I know it could be a structure of, 3 or 4 fields. Then it checks that the original version, I guess it could check before, but what's written here is sufficient. It checks that the version is not locked, so it's even, okay? Then it also checks that the version hasn't changed. So if either the version is locked or the version has changed from when you first read it until you now read, doing the version check a second time, then it fails. And what fail means is it retries. Notice it's in a while loop. But if those 2 tests both succeed, then you just return the value and you're happy. Basically, it says that no one has updated it in the interim between when you first read the version and you second read it. The CAS is a little more complicated. Let's ignore the first handful of lines, but you'll notice that there's a version CAS where basically that's the lock, where it converts from ver to ver plus 1. So that's going to take an odd number and convert it to an even number. And then it's going to, if that succeeds, if it succeeds on taking the lock, then it's going to basically check the value. If it's equal to the old, then it's going to update it, and then it's going to unlock and return, whether it succeeded or not. And if the CAS didn't succeed, it returns false. The reason this is correct might be a little subtle, so I'm not going to go into it. But yeah, you don't have to loop on this. Although there is a while loop, if you notice on the 3rd line, there's what wait and lock. So this is actually locked, which could while loop forever. So this could block both the CAS and the load could loop forever if some thread stops. So that's the idea. So
Guy,
yes,
I'm sorry to interrupt. Just it's 4:55, and I just wanted to check with you about your sense of how much more.
Yeah,
there
I
is
think
to
this is
talk.
basically. I have 2 more slides.
Oh, okay.
So then the conclusion. Yeah.
Great. Thank you.
So the idea here is to make this lock free. We basically combine the 2 ideas, and I'm especially given the lack of time. Let me just at a very high level, the idea is you have both a version number and also this indirection pointer. And the indirection pointer is only used temporarily while you do the update. So what you basically do is when you come in to make an update, you actually allocate an extra copy. You have this pointer point to it, but then you immediately copy it into this direct data here. Okay. And if this all happens, successfully, then you basically uninstall the pointer, and then any reader is going to be able to read it directly from the data. So the point is that most readers are going to capture this, if there's not some huge amount of contention, most readers are going to be able to read it directly via the data. And if not, there's always this backup version in pointer that they can read. And that's what allows you to make it lock-free. So I'm not going to have time to go into details, but that's the high-level notion of how it works. There are many subtle points about this, and it's actually not trivial to prove this is correct. But I guess the point being that we only have to prove it correct with this one operation, and not for every single data structure that might need it. There's some performance numbers, and there is some overhead of this level, versus if you look at it versus seek lock, the seek lock is red, And the black is the most efficient version of our data structure. Let's ignore, well, the other one to look at is Libotonic, the pink one at the bottom, just to see how bad the C++ implementation is. But yeah, if we concentrate on the red and the black, you'll see the red is a little bit better when you're not oversubscribed, because the locks aren't harming you. But as soon as you go to oversubscription, then this lock-free version, has significantly improved. So it's more robust against oversubscriptions. Okay, so that's all I was going to say about big atomics, and I am at my conclusion 2 minutes early, I guess.
There's a question actually, Guy.
Yep.
Regarding the overhead, is it due to safe memory reclamation techniques from the indirection?
Well, actually, it turns out that I didn't show the code for the load or describe how the load works. The load, as long as it can read a direct, doesn't need the safe memory reclamation. And that's part of the reason it's not worse. So I guess the point being is, if it always had on every read to do the safe memory reclamation, which would be some sort of grab an epoch counter, it would actually be a lot worse than this. So the overhead is, this is 50% updates, and it's just from the fact that the update is more complicated because, and also the update does have the memory reclamation overhead. The update has to update both this indirect pointer and the direct pointer. In fact, if you make that U 50%, the U means the percentage of updates versus CAS, if you make that smaller, then this overhead goes down. In fact, if you make it all reads, then the overhead is 0, because it always goes to the fast. The fast path is the one way it can just find the direct value.
Thank you. And now there's another question. You mentioned earlier in the talk about some published papers that were not entirely correct. And so there's a question about how has your work been verified? Is there a formal verification effort?
There is not one, but one of the my co-authors at the beginning, Siddhartha Jayanti, who might be on this call, we've been working on, in particular, looking at some of verifying some of these, and the in particular big atomics. We would like to verify that. We're looking, and we would, and the lock-free locks as well. So that's future work, but I do think it's important to verify these things, given, I hope that none of these things are incorrect, but until we formally verified it, I'm not 100% sure, just
Okay.
99.
And there's a follow-up question. Michelle, are you able to unmute? I think maybe you could ask this better yourself.
Yes, I can ask directly. It's going back to the log-free lock. When you do a store, do you need just the cast on the log followed by a regular write, or do you need 2 casts? And if you need 2 casts, how is the atomicity achieved?
No, you need 2 separate casts, but they don't have to. It doesn't have to be a 2 cast, a decast. So you can do 1 cast. The 2 casts don't have to be atomic together.
So,
yes,
so why do you need the second? If you
on the
succeed
log,
on the cast on the log, why do you need the second cast?
You need the CAS on the actual location. So the log, you're casing the old value, and then you need a CAS to store it, to do the store itself.
Oh, that's to guard again stores from outside the thunk, I suppose, from elsewhere.
Yes,
Okay,
yeah, because someone else could be doing a store at the same time, and you have to make sure.
Yeah.
Yes.
The questions are rolling in. Here's one more. In the first 2 pieces of work, the approach was to take some existing code and touch it up a little bit with new data structures to get certain properties. Does it make sense to revisit the quote optimized implementations with your new data structures to get some more performance?
The optimized implementations. I'm not sure. Sorry.
Rohan, would you like to unmute and clarify?
Yeah, so I guess, for example, one of the, some of the data structures you talked about, you were comparing against some optimized lock-free BST or something, but you were able to compete with it by taking a kind of simple, maybe lock, with locks BST and then adding some special pointers into it. Could you sort of take that optimized BST, the optimized lock-free BST, and maybe give it these data structures and do something a bit different to get even more performance, or kind of that doesn't quite make sense?
Well, the code that we're starting with is the lock-based code. And sometimes the lock-based code is faster, and sometimes the lock-free code is fast. In the case of the Harris linked list, it's particularly fast, and it's faster than any lock-based code. Now, we started with the fastest lock-based code, which is also optimized, and then we added our lock-free locks. But even that was the lock-based code was already slower than the lock-free code. Partly because just linked lists are so simple. That's not necessarily true with the trees. In fact, I think our lock-free trees are more efficient than any, or certainly equally efficient as any of the lock-based, lock-free, existing lock-free codes.
So we're a little bit past 5, and if people have more questions, Guy, can they reach out to you after the talk?
Yes. Sure,
Okay.
of course.
So I'll let you finally get to your concluding slide, and then we'll close.
Okay. Well, the concluding side is, right, it's just saying there's many opportunities. I encourage people to look at these, general purpose approaches instead of just, knocking one data structure off after the next. And I guess, the goal here is not just to have a general purpose technique, because it's not too hard to come up with some, universal approach that will make everything lock-free. In fact, it's well known that you can universally make anything lock-free. It also has to be efficient. And I think it's the combination of these that's important. So having a general approach that's also efficient. And that's it.
All right, we got a question from Charles that I'll have as a closer. What kind of linguistic support would help?
What kind of linguistic support? Well, I guess like just the try-lock is a little ugly because you have to like wrap it into stunk. And so you have to use a lambda, in C++, you have to use a lambda and, all the crafty part. So I guess if you were going to design this directly into a language, you could, just say, critical section, and then have the critical code without wrapping it into a lambda, etc. If that's what you're, asking about, whether there could be linguistic support in languages, certainly there's that flavor. There's quite a few.
Thank you very much, Guy, for a very interesting talk, and thank you everybody for your questions. And that's wrapping up our seminar for today. And we'll post the recording, and we'll see you next month for Mike Spear. And thank you once again, Guy. Really appreciate your talk.
Thank you,
Okay,
guys.
thank you. Okay, thank you. Bye, everyone.